our next question, which is now that we understand essentially what is the best RF band, what is the need for an RF band or to transmit at RF bands, what is the best one? We've been searching for RF bands since Marconi did the first transmission, or even before that. Did we find it? And if yes, which one is that? So very briefly, the idea is that there are multiple different bands that are available, and there are multiple different systems that work in those bands, all the way from RF down to basically optical systems even. Now, if we look at the RF bands in a slightly more detailed fashion, we will find out that there are useful bands essentially in the order of gigahertz or even below gigahertz. And nowadays, as we just discussed, we're moving towards higher frequencies that may actually approach 30 gigahertz, 40 gigahertz. As I said, for 5G, there is already actually licensing that has occurred in those bands. And eventually, we could reach even 40 or 60 or even 80 and frequencies above that. So what really dictates what is the right band for your application? Because the reality is there is no such thing as the best band. There is simply an appropriate band for the application you're targeting. So let me give you a few different scenarios. So one of the scenarios is that you probably have to work in RF signals in a rural area. There, life tends to be nice. Over fields, signals don't get attenuated very much. And what we do in those cases is that we try to look at signals that are relatively low frequencies, large wavelengths. Because they go farther, or if you want to restrict it, then you basically choose higher frequency because higher frequency gets more attenuated. In urban areas, the situation is slightly more complicated because you have to take into account those annoying things called buildings. And buildings tend to attenuate signals, they tend to reflect signals. So there's a whole area of RF propagation, which I kind of only mentioned last time, which dramatically depends on frequencies. So some type of an urban planning also goes on when you decide actually what to do. But more importantly than that, when we decide about RF bands, we have to consider questions such as what is the data rate that you want to have in your network, and what is the number of users that you need to serve. So let me give you some ideas of what I mean by that. There is something called Shannon's formula, which actually gives you a good idea about what we call channel capacity. So channel capacity is essentially a number which basically tells you how many bits per second you can basically transmit. And that's important, right? Because if you want to transmit and download, let's say, a high-definition movie in 1 minute, then you have to basically calculate how many bits is the movie and then download it. And then you have to basically have so many bits per second for the movie to download within 1 minute. So this channel capacity is related to the bandwidth of the channel B. It's also related to the signal-to-noise ratio, as we're going to see later on, of your signal. Signal-to-noise ratio is simply a ratio of your signal strength over your noise. So if you look at this very simple formula, which is a theoretical formula, it gives you a limit, and now modern systems get close to that limit, you will find out that you have basically two main knobs to tune if you want to transmit more bits per second. The first knob is your bandwidth. The second knob is your signal-to-noise ratio. Now, the signal-to-noise ratio is under a log, so clearly the bandwidth is a lot more influential. So one can say, great, increase the bandwidth. But as we just discussed, increasing the bandwidth comes with a lot of issues. So increasing the bandwidth is great, and this bandwidth here is literally in hertz. So one way to increase the bandwidth and not get penalized by increasing your fractional bandwidth is to simply increase B, but at the same time increase your center frequency as well. Let me tell you what I mean. If I'm trying to transmit 1 megahertz and my center frequency is 100 megahertz, then my fractional bandwidth here is basically 1%. Let me make that a bit more clear. But if I'm trying to transmit 1 gigahertz bandwidth and my center frequency now is 100 gigahertz, my fractional bandwidth is still 1%. That means the same antenna that worked for this guy will also work for this guy because the fractional bandwidth is the same. But clearly, when I have a bandwidth of 1 gigahertz, I can transmit, according to this channel capacity formula, 1,000 times more bits per second than I could transmit before. So what people say is, wonderful, increase your B, that means go to higher frequencies. So one of the main drivers that basically push our systems today to go higher and higher frequency is precisely the need to get faster and faster data rates. And in fact, that's one of the reasons why we're exploring those type of 5G bands, is because in those bands, my fractional bandwidth can be small, but my absolute bandwidth can be very, very wide, which means I can transmit a lot of bits per second. So the other reason why we actually push frequencies to really high frequencies is because anything at the low bands has already been occupied. That's called spectrum crowding, meaning that we're not the first people who think about radio. The previous generations also thought about radio. It turned out that making transmitters at 30 megahertz or 300 megahertz or even below that was actually far easier than making transmitters at 1 gigahertz or 30 gigahertz. So early pioneers made the transmitters and the systems to work at low frequencies. They occupied all of those bands. Now we were born, only bands that are free are the higher frequency ones. So tough luck, you have to learn how to work at higher bands. Finally, there is a reason for sometimes picking a peculiar frequency because the atmosphere has peculiar characteristics around that frequency. There is a very well-known, for example, attenuation spectrum that will happen around 60 gigahertz. So it turns out that the oxygen absorption at 60 gigahertz is very high. So if you were to build actually a Wi-Fi router in this room today at 60 gigahertz and you were to transmit it, the signal would suffer a huge amount of loss as a function of distance versus if you were to just build this thing, let's say, at 50 gigahertz, simply because the oxygen molecules resonate and absorb the frequency at that point. And yet, we still design 60 gigahertz systems. Why? Well, the reason is because sometimes we actually do want this attenuation. If I want to cover only this room, for example, and somebody else wants to cover the room next door, we can both use 60 gigahertz and make sure that my signal is so much attenuated by the time it goes to the next room that they actually don't care about it. So by picking the right frequency, sometimes we can actually solve a lot of problems that would have been solved otherwise. So special atmospheric conditions sometimes make us choose frequencies that we wouldn't have thought otherwise.